All right, thank you very much. And, everyone should recognize this picture by now. I just wanted to put it up to indicate that I'm going to be talking about LIGO. But the first thing that I want to say is thank you to the Black Hole Initiative for inviting me. But also, I didn't finish this sentence, but I don't know if people have heard, but in Hanford, Washington, a tunnel has just collapsed in a nuclear waste facility. And there's now been declared a state of emergency, so, and at one of the sites of the LIGO project, so it's sort of breaking news that's happening. Okay. So what I want to do, I think, is going to be a really, really hard sell. I want to argue that philosophers should engage more with empirical science and experimental science. I know that everyone's going to immediately say, like, surely not, right? That's a terrible idea. But what I want to do is to argue, first of all, that philosophers who are studying philosophy of science and modeling should engage with what I want to call, following Larry Loudon, the context of pursuit. For a long time, people in philosophy have made a distinction between what they call the context of discovery and the context of justification. This is a well-known distinction that began with Hans Reichenbach in the book Experience and Prediction. And in the context of discovery, that's the process of actually finding things out. It's usually been considered to be sort of anarchic and contingent and irritating. You look for something and you don't find it, and then your worst enemy finds it, and it's sorts of interesting stories that everyone knows from the history of science. And then in the context of justification, you rationally reconstruct, that's a phrase from Rudolf Carnap, and you justify your results. You write them up nicely as if they just followed quite clearly from a few formal relationships, and you discovered them over your morning coffee, right? I mean, so this is the distinction as it was originally drawn. And this presents the process of discovery. It sort of goes back and presents the process of finding things out as rational, smooth, and quick, right? So instead of the actual messiness or the actual difficulty, it presents it as being this sort of easy process. Larry Loudon in Progress and Its Problems and Alan Franklin in The Rise and Fall of the Fifth Force have identified a third context, which they think is equally important, the context of pursuit. And that's the context in which you have a theory or an idea and you consider it worth pursuing. And when you focus on the context of pursuit, you study what I call heuristics, or what others call heuristics, namely which methods and techniques allow for hypothesis testing, the expansion of theories, model construction, the progress that gets made. And what I'm focusing on in my research at the moment is heuristic models. And in that respect, this is where I argue that focusing on experimental science and its role in theory building has a payoff. You learn about how models are generated from data and theories from testing, which elements of a theory or model depend on which other elements, and how each element of a theory or model can be regarded as part of a class of such elements, and what the principle of membership in the class is. So if you take black holes, a Kerr black hole is a member of a class that also includes Schwarzschild black holes, which have no charge or momentum, and which kind of black hole any given black hole is depends on properties like mass, charge, and spin. I am not telling anyone in this room anything. This is very elementary, but it's significant to determining what the classes of objects are in the theory that we're looking at. I'm going to talk today about the LIGO detection, and I'm going to talk about an area in which I think that heuristics is making a lot of progress, but I'm not sure that it's been really brought to the forefront recently, and so this is what I want to talk about. And so the first thing I want to talk about is just in general detection. I think every detection encodes a kind of information. It doesn't just encode information about the target system, but also about the detector itself. There's been a lot of work in philosophy, Patrick Suppies and others have worked on, you have to have a model of the detector, you have to have a model of the data, the possible ways of generating models of the data, and of the systems under investigation. And then that process allows for the estimation of the system parameters. And this is something that the LIGO researchers, some of whom are in this room, know extremely well. There's been a recent paper called Tests of General Relativity using GW 150914, that proposes ways of estimating parameters of the binary black hole system that was observed using the data. The LIGO sessions in this conference have mentioned other means of testing. I'm just going to quickly summarize them. Emanuela Berti and Deirdre Shoemaker have talked about whether or not a black hole is a Kerr mass or not. Shepard Doleman and others, Dan Holtz, Scott Hughes, and Matthew Evans have talked about improved detecting procedures that will allow for cross-confirmation across detectors, and also more comprehensive scanning, better localization, and direct observation. And here I'm just going to shamelessly steal Emanuela Berti's entire slide, talking about ways of, with attribution, I hasten to add, talking about ways of probing general relativity and probing beyond standard model physics using the LIGO results. I want to focus on the path from the data to the waveform. That's what I've been looking at recently, and it has a truly amazing history. I mean, most of you know it better than I do. I can't talk about it entirely here, but I want to talk about that. And so I just want to quickly begin with the fact that this is, again, we begin with data, right? I mean, we begin with interferometer data that's registered at the interferometers in Hanford, Washington, and in Livingston. The incredibly tiny wave strain is picked up by the interferometers, and the data ends up looking like this. It's time series data. The LIGO researchers have been incredibly open about allowing their research to be downloaded by others. Thank you very much. And then you end up with waveforms. You have predicted waveforms that are constructed via numerical relativity, which was talked about by Deirdre Shoemaker earlier. And you go from the data to the waveform. Again, I can't talk about this in great detail, but there are many ways of doing this. And then you end up, I don't know whether this is going to, yeah, this is not going to make a noise, but you end up with a chirping system. Okay, and this is the YouTube video that LIGO has made available of how it chirps. Okay, so first of all, how does the data, according to the LIGO researchers, and those of you who are here can give more information or maybe probe in the question period, or maybe tell me in the question period. One way that the LIGO results test general relativity is that if we can infer that the orbital period of the observed binary system isn't constant, then that gives us a test. So in this recent paper, the argument is that in Newtonian gravity, binary systems have constant orbital period, whereas in general relativity, the binary's orbital period decreases over time as the energy and angular momentum are rotated away. So this gives you the constancy or not of the orbital period gives you a test. This is something that you can find in the data. But in order to estimate the orbital period, you have to have a good estimate for the waveform. The waveform, in turn, depends on the chirp mass of the binary system, the symmetric mass ratio, and the angular momentum of the compact objects, et cetera, et cetera. The search parameter space is thus defined by the limits placed on the compact objects' masses and spins. So the way that searches are formed is partly by providing well-founded limits for the masses and spins of the objects that are being looked for. What I want to focus on is some recent work by Erik Chassand-Motin, Patrick Flandrin, I'm doing my best, and Archana Pai, and others who've made contributions to the study of chirping systems in general, and in particular to detection and to signal processing. Because this, to me, and Alessandra Bonanno at Munich and others working on LIGO have investigated the implications for future data analysis and for mathematical modeling. So a while ago in 1999, Chassand-Motin and Flandrin wrote a paper called On the Time Frequency Detection of Chirps. And they were really looking at analysis of time series and analysis of time frequency signal detection. And they said and they focused on this question, which from a philosophical perspective is fascinating. As far as detection itself is concerned, from a signal processing point of view, a key question is to get some a priori information about possible structures for the expected waveforms. So in order to have the best standards for detection, you want to have some kind of structure of expectation for the waveform. A wide variety of situations can be considered, each corresponding to different types of signals. This was all the way back in '99. And then they looked at, this is going to be maybe a bit hard to see, but on the left, they have the qualitative validity of the chirp interpretation for gravitational waves. And this diagram plots a critical frequency, which depends on the masses of the binary system. So this is what we were talking about. This is how this is critical frequency, the limits within which the systems can be detected. And this gives you a kind of a sense of the space within which these limits can be defined. And then on the bottom right, this is figure 5, detection of a gravitational wave. And it illustrates the efficiency of an optimum time frequency-based detection for a gravitational wave. And it gives you, once you have a model of the detector and a model of the expected value for the wave, these are, this is a model of what can be detected. So what they were trying to do all the way back in 1999 was to find a sense of the space within which the waveforms can be detected by a given detector and what the expected values would be. Yeah, and in the examples of figure 5, the one on the right, the chirp mass was implicitly assumed to be known. So this was a set of assumed waveforms for a given known chirp mass. And in 1999, Chassagne, Montin, and Flandrin basically said, well, let's take the question, what if we don't know what the chirp mass is? Is it possible to classify a set of expected waveforms with unknown chirp masses, right? So is it possible to, and the answer to that was yes. In 2006, they published a paper on what they call the best chirplet chain method, which I like as a title, near optimal detection of gravitational wave chirps. And here, they introduce a general chirp model and claim that it includes all physically realistic gravitational wave chirps. This is a very ambitious project. And the argument is that you take what's called a chirplet, which is a short piece of signal whose frequency varies linearly between two successive nodes of the grid, and you provide a finite grid of template waveforms, which samples the set of possible chirps. So the idea is that you have an a priori classification of chirping systems using this set of templates. I can't obviously explain how they try to do this, but this is the idea. This is what they want to do. Now, if this works, right? I mean, of course, if this works, then this is basically a way. What you do is you generate these template waveforms, and they then give you templates for matched filtering of the signal. And this is then matched filtering with a model of the detector and a classification of the chirps that is possible to detect. It's based on a model of how different chirping systems can be detected given detector sensitivity, right? Given a particular detector, which systems can you detect with it, given different physically realistic values, and a classification of chirping systems and exactly how they're modeled, whether using best chirplet chains or other methods. A logical way to move forward from this, if it does already work, would be to begin with a template bank mentioned in that previous slide, and then to build a family of models of binary black hole system dynamics based on physically realistic values of the parameters. I don't even know whether that's possible, but since I'm a philosopher, I get to speculate about entirely imaginary things, and then you get to tell me that it's not possible. Okay, so what do I want to say about this? The particular analysis that I've given, even though I did give a particular analysis, is not in fact the only point. The point is that what philosophers usually do is ignore the case where you don't already have a formal theory that gives deductive results already. They ignore the case, they don't all do this, but it's the case that most philosophers don't focus on the models that are developed and the systems of classification that are developed in the process of experimental research in physics. But if you don't focus on experimental work being done and on the development of theoretical and formal tools that are embedded in that experimental work and research on the ground, you're going to miss a great deal. Focusing only on what philosophers call the context of justification misses all of the material in the context of pursuit. For instance, a lot depends in contemporary philosophy on the way that a scientific classification is set up. So you could look at the way that our classification of chirping systems is set up, the way the classification of black holes as Kerr or not is set up, but you can also look at, for instance, people talk about dynamical systems, and that's another one of the analysanda. I'm almost finished. This material is crucial for contemporary scientific theories about realism, which often depend on scientific classifications and whether they persist in different scientific theories or not. You may not realize this, but when you set up a classification in a system, philosophers 100 years from now will argue that if that classification persists, that's a reason that the things that that classification refers to are part of reality. So you actually have the power to create reality, which is kind of a great thing, because it's often in an argument. It's called methodological realism in contemporary philosophy of science. It's an argument that if a particular structure or classification persists in scientific theories, that's a real, the best explanation for its persistence is that it's real. And so analyzing how scientific classifications are set up in the first place, how we first come up with families of systems and so forth, is a really fascinating question philosophically, because in some ways it's how people think that our access to reality is founded philosophically. The work here provides an a priori framework for detecting and modeling of the data. This is a step forward. LIGO is unparalleled. I don't think I need to tell anyone that. And in the future, the LIGO experiments are the tip of the iceberg. LISA, Virgo, Cargo, the Event Horizon Telescope are undertaking more and more ambitious experiments. These experiments provide data that can be I'm not even going to read that sentence, but one way for philosophers to work in a way that I hope is complementary to scientific research is to focus on how we can learn from the data and how it's modeled, and on how the dynamics of experimental research informs theory building. And I'll stop there. Thank you.
Thank you, Lydia.
Thank you.
We have time for some questions. Andy and then Jeroen.
Is the statement that if you invent a classification and it persists for many decades, it's therefore real, is that more than a definition of what the word real means? In this context?
In this context, yes. It is well, it depends on who you're talking to, but so I can talk in great detail about who has said this. So there are people, Statistical, for instance, is one of the contemporary philosophers who makes this argument. But
there's some other definition of the word real that...
So the definition of scientific realism that's usually being used is one from Bas van Fraassen, who ironically is an anti-realist. But the definition is that scientific theories are literally true, and the statements of scientific theories are literally true statements of what is actually in the world. And so the furniture of the world is, electrons, fields, and so forth. That is what reality is. Does that answer your question?
It seems contradictory. Right, because we could invent a classification, have it persist for decades by some combination of brainwashing and force of personality and
yes, grant funding.
Grant funding.
Yes, no, well, I mean, but philosophers don't believe that. Many philosophers don't believe that, because the argument is that, look, you would try to do that, right? I mean, you could be a really charismatic person, and you could really try to do that. But if your classification just fundamentally didn't work, eventually some postdoc, would sort of make their career by proving you wrong. And the argument by philosophers is that that's just inevitable, right? That's just going to happen. And 20 years, 30 years, it doesn't matter. Yeah.
Hacking had the view that this was true of social categories, like, say, if you name something a psychoanalytic category, of a certain kind of criminality, for instance, that it would shape how people saw themselves and therefore create the category that was named. That you could actually create the laws and institutions, yes. You could incarcerate people who saw themselves as X or Y and that. But he actually thought that was not so for physical objects. So he made a differentiation between a naming that shaped the self-concept of people in the human sciences and electrons, which didn't have a particularly well-developed sense of self. Erwin, please.
Granted, this is a black hole symposium,
Yes.
but how would you contrast your philosophy as applied to LIGO, say, with applied to the Large Hadron Collector experiments?
Well, I would say that the methodology would be the same, right? I mean, but I think that because I would still say, look, I mean, the way that I was trained to approach these things is to begin with the observation, right? Begin with the data, and then look at how, in particular, the data is used to support conclusions. And I tend to be very pluralistic about the methods that are used. So I mean, the methodology would be the same. I would say, how are these categories being constructed? How are models being constructed? And so in a way, I would have to be like my friend Michaela Massimi, who's basically embedded herself in the Large Hadron, in CERN, actually, not the Large Hadron Collider, but in CERN, and is observing what's happening. And I think that we have a similar approach to this idea that you sort of look at how people are making the moves that they make, and then observe it. We're sort of watching what happens. Yeah.
Priya, Volker, and then
Hi, very interesting, Lydia. So I was very curious whether, this interesting category of simulations, as you saw both with LIGO and Event Horizon Telescope and so on.
Yes.
Right, so simulations have become the sort of intermediary, right, between reality because they are shaping what you expect to measure or observe. So I was curious to hear, do you collapse simulations into your general idea of models, or do you see them as something else? Do they mediate reality? Because
Yes.
this reminded me of what Shep was saying earlier, right? Like, hold your horses, guys. You cannot just see quite what the simulations are telling us. So.
Yeah, no, that is the question to me of my research right now. I mean, so because there's another person I work with sometimes, Elisa Bokulich at Boston University, who's a fictionalist, right? So she argues that it's possible to have a false model that nonetheless sort of captures what you want. And then the question is, do you want to then be committed to the reality of that false model, even though you know it's false, right? Like, you made it up to be false. It's deliberately false, like the Bohr, yeah. So that's the idea, right? And so the question is, if you have something that's a simulation, to me, simulations can perform multiple roles, and that's what I'm really thinking through right now, and so I'd be very interested to hear what people have to say about it. One of the roles is providing standards. Right, so I think that in some cases you have a fictional model that nonetheless provides a standard for comparison between models, or it provides a way to say, well, this is how we can actually represent this model as being derived from the formal relations of the theory. And so you can in some cases you can only do a regression if you have a simulation, right? I mean, so there are cases where you can say this is a different role for simulations, but they don't have to be considered as entirely fictional in that case.
Because they can arbitrate between theories, competing theories, right?
Precisely, yes. And they can and between theory and evidence. Exactly, yeah.
Volker, with the official timekeeper, tell me, how are we doing? It's okay?
So Lydia, so the act of classifying creates reality, for better or worse. So what would happen to the world if we as scientific community would stop classifying? Would happen anything?
You'd stop classifying. That is a really interesting question, because so just a super brief history, right? Larry Loudon has a paper called The Confutation of Convergent Realism, where he gives this argument that's usually called the pessimistic meta-induction. He says, scientists have produced all of these classifications, the ether, phlogiston, all these, and he says, there's something interesting about the ether and phlogiston and caloric and, which is that none of them are used anymore, right? None of them are any longer considered to refer. And he says, so we can assume that every current classification is also going to be sort of no longer referring. As you can imagine, this is an anti-realist argument, or it's usually taken to be one. And so the question of, what if scientists just started saying, like Ernst Mach, for instance, said, let's just use categories that we consider to be convenient sort of cuts in the data, right? They're like the principles of filing, you know, like we file this away here, we file that away here, but we don't consider that to be a real classification. I mean, I think then it's possible that could happen. But scientific realists think that it's not possible. They think that what's happening when scientists work with the world is that they're working with the things that are really out there, and that the only way that science can get closer to the truth or can make progress is by latching on to what's really there, sort of latching on to these underlying structures. So the argument from their case, from their point of view, is that science would stop making progress.
I just wanted to point out that there are two worrisome phenomena that perhaps you might want to consider in modern science. One is
Yes.
we are getting to the regime where there is big data, a lot of data that we cannot store, and therefore we throw most of it. And CERN is a good example, and so we need to anticipate in a way what to keep. And when you anticipate, you
Yes.
can throw the baby with the bathtub water. That's point number one. So our sense of reality is shaped by what we perceive to be reality in the first place. But the second comment is that there are parts of the physics community that do not interact with data at all. They're completely divorced from the feedback that data gives them. And so I wonder, how would you regard the physics derived this way without any contact with data?
No, the first point, yeah, that's fascinating, because partly the question of, you know, what is, like when you think about what would you save from the fire in your house, you know, I mean, it's kind of that, what do you save from big data is determined by what you already think is significant, and that's a really big problem. But yes, the question of if you have physics that's entirely, I wouldn't say, it's not cut off from the data entirely, right? But it's done without the data, right? I mean, so it's definitely, I mean, and that was, in a sense, what I'm talking about now is I'm trying to be a corrective, but that was how philosophy of science is done in some communities for quite a while, right? I mean, people were working on theoretical physics as their sort of template for scientific investigation. And my argument is really that that's shaped the way that philosophers see science. They see science that doesn't work with data as or in the past, those philosophers have seen science that doesn't work with data as kind of the paradigm for scientific research overall. And so in a way, I'm just trying to push more towards arguing for engagement with the data, not against engaging with theoretical physics, because I think that's crucial, obviously.
I'll begin with two caveats. The first is I don't have any cool pictures or movies or videos or anything like that, so just a lot of plain text. The second is perhaps more serious. If everything goes as planned, this is going to be a very contentious and provocative talk. In fact, I think I can safely say that for those among you who think about topics related to this, I'm pretty sure not a single person will agree with me. And so you may wonder why I'm giving this talk at all. Well, for three reasons. One, I'm just kind of an ornery, contrary person to start with. So, you know, this is my nature. Two, I actually think I'm going to be arguing against a kind of orthodoxy and folklore in the field. I'm going to be arguing against something that has been assumed for so long that people, I think, forget that it even is an assumption. And I very much see one of the jobs of a philosopher is to act as Socratic gadfly, to get us to at least to look at, remember, and appreciate that there are these assumptions that are very widely shared, very deeply held, and almost never even recognized as such, and certainly very rarely questioned. So that's a large part of the point of this talk is just to get people to think again about why it is certain beliefs are held, are very widely held. The third reason is that I actually kind of sometimes half believe this. So maybe I will sort of half convince some of you. So caveat lector atque spectator. So the current state of play in physics is that when we're talking about black hole thermodynamics, the focus has been on quantum properties and effects. There's nothing of thermodynamic interest in a purely classical treatment of black holes. You know, they're the four laws of black hole mechanics. They are derived in the purely classical regime. They are in perfect formal analogy with the four laws of black hole thermodynamics, but it's purely formal analogy. One has to take quantum mechanics into account to really conclude that black holes are thermodynamical objects in a rich, physically substantive way. I will argue to the contrary, that I think it is in fact possible to construct a physically rich, physically significant thermodynamical theory of classical black holes. And if that's right, that shows that there's already a very deep relation between gravitation and thermodynamics on their own, completely independent of the relationship of either one to quantum mechanics. I think that would be an incredibly interesting conclusion if my arguments are correct. So what is the status of the analogy between the laws of classical black hole mechanics and the ordinary laws of thermodynamics? Are they just formal analogy? I mean, this happens all the time in physics. I mean, everything and its mother is a simple harmonic oscillator. That doesn't mean that we think that pendulums and electrical circuits and vibrating strings are all the same kind of thing. So the mere fact that there's a perfect mathematical formal isomorphism between the two sets of laws, well, that may not tell us anything of physical significance. Or the other possibility is that we may in fact have to conclude that the laws of black hole mechanics are in fact the laws of thermodynamics extended into a new regime, in very much the way that at the end of the 19th century it was realized after a long struggle, along both conceptual, physical, and mathematical struggle, that one had to extend the laws of classical thermodynamics into the regime of electromagnetic radiation. Otherwise, inconsistencies followed. One would lose the second law, for instance, if this weren't done. So the standard argument is no. It's a purely formal analogy. Very crudely speaking, the standard argument goes as follows, when people even make the arguments. Classical black holes are perfect absorbers, therefore they must have physical temperature absolute zero. If you look at the literature, especially in the 70s and 80s, you can see many of the greatest general relativists and physicists making essentially exactly this argument. So, and there is, I think, it's not something to dismiss out of hand. There is something important here. I mean, if you want to be a little more precise, say put a black hole immersed in thermal radiation in a reflecting box, the black hole will perfectly absorb all the radiation, emit none. Therefore, the temperature of the black hole has to be absolute zero. Well, and then secondly, there's the problem of physical dimension in the classical regime. The physical dimension of temperature is, in geometrized units, is mass. The physical dimension of entropy is dimensionless, it's a pure scalar. But the physical dimension of surface gravity, kappa, of the black hole, which is standardly taken to be the temperature of the black hole, is the inverse of mass. And the physical dimension of area, of course, is mass squared. And in classical physics, one has no dimensionful constant no dimensionful universal constant to use as a factor to get the correct dimensions, to make kappa a real temperature, have it have the proper physical dimension of a temperature, and similarly for alpha for area as entropy. And therefore, one must invoke quantum mechanics. The derivation of Hawking radiation to show it really has a temperature, the natural introduction of h bar to give the right physical dimensions, to justify the claim that kappa is a physical temperature and area is a physical entropy. Well, I think the standard argument actually misses some real physics, because a black hole immersed in thermal radiation in a box will emit energy, in fact. Falling thermal radiation perturbs the black hole, causing it to emit gravitational radiation, which physically couples with the thermal radiation outside the box. Classical black holes are not perfect absorbers. Of course, they don't emit electromagnetic radiation, but electromagnetic radiation, if we're talking about whether or not black holes are thermodynamical objects, and whether or not black holes as thermodynamical objects couple thermally with other kinds of systems you already think of as thermodynamical objects, electromagnetic radiation is not the proper medium for thermal coupling. Gravitational energy should be the proper medium for thermal coupling, because black holes are purely gravitational systems. So just as happened, again, at the end of the 19th century, with black body radiation, we need to amend the physical concept of thermal coupling. Before it was recognized that black body radiation was a kind of heat, or at least could possess a form of thermalized, a real thermalized energy, a kind of heat. The only kind of thermal contact, thermal coupling people knew of was direct contact. Bodies were thermally coupled only when they were directly contiguous to each other. Then black body radiation was realized to be thermodynamical. That broadened the concept of thermal coupling. Bodies could now thermally couple when they were spatially separated by the exchange of electromagnetic radiation. So perhaps if we want to think of black holes, classical black holes, as thermodynamical objects and ask whether they thermally couple with other systems we already think of as thermodynamical, then perhaps the proper medium for that should be some exchange of gravitational energy, not electromagnetic energy or energy encoded in other types of quantum fields. I'll also just mention as an aside, you can ask me about this in question and answer if you want. I actually don't think that the derivation of Hawking radiation as a justification for attributing a physical temperature to a black hole is nearly as good an argument as people seem to think it is. But I'll put that aside. So let's engage in some counterfactual history. Imagine we knew only general relativity and classical thermodynamics. We knew the 4 laws of black hole mechanics. We knew the laws of thermodynamics. We knew nothing about quantum mechanics. How would we decide whether or not black holes were truly thermodynamical objects? Well, I say we would do it in exactly the same way that the guys in the 19th century decided that black body radiation was thermodynamical. They asked themselves, does this particular function of the power spectrum of electromagnetic radiation, can it be introduced in the same way, and does it play the same formal role as temperature? But even more importantly, does it mediate couplings between electromagnetic radiation and ordinary thermodynamical systems in the same way as ordinary temperature and entropy do? And in order to argue, if I can make a decent argument to that effect, that in fact, when you appropriately set up a kind of interaction between an ordinary thermodynamical system and a classical black hole, then surface gravity and area do couple with temperature and entropy of these ordinary systems in the appropriate way. And I think if that is correct, there are no grounds for saying that that classical black holes are not truly thermodynamical systems. So the process I call it shouldn't be reversible there. It's only reversible for Kerr, and I'm not doing Kerr, I'm only doing Schwarzschild. So just ignore the word reversible. Although it is reversible, actually this is an interesting point. It's reversible in the sense that it's isentropic, but it's not physically reversible. So this is actually one place where black hole thermodynamics deviates from ordinary thermodynamics. We normally think of as an isentropic process as one that is at least in principle physically reversible. That's not true for black holes. That actually raises an interesting point about how learning more or trying to understand more about the thermodynamics of classical black holes might give us some hints about what kinds of constraints one has to place on an underlying statistical theory in order for that statistical theory to recover what we think of as the thermodynamical behavior of black holes. But again, that's far beyond the scope of this talk. So I call it the Carnot-Gauroch cycle because it's kind of a mongrel mix between a true Carnot cycle and an infamous thought experiment that Bob Gauroch gave in a seminar in Princeton in 1970, in which he exactly argued, using this infamous thought experiment, that black holes, if attributed to temperature at all, should have a temperature of absolute 0. And I kind of like this, that I'm using it here, because I'm using his process, because if I'm right, it's kind of a jiu-jitsu move against Bob. I'm using his original argument that you shouldn't attribute a temperature to black holes to an argument fact that you should. So start with an empty box at infinity. One side's a piston. Quasi-statically fill the box with fluid from a heat bath at fixed temperature. When the piston is withdrawn part of the way, seal the box. The box now has total energy depending on rest mass, temperature, entropy, and work done. Quasi-statically lower the box towards the black hole, extracting work from its gravitational energy as you go. Perhaps the rope is hanging over a pulley and it's attached to something that has some friction. So as it slows, does that mean I have 5 minutes left? Yeah. So as the rope very slowly goes, it is rubbing against the surface of the friction, and you're extracting some heat from it. You're heating your cup of coffee, or you're using it to lift a weight, whatever. So the important point is that an observer inside the box, co-moving with the box, sees nothing change. At infinity, when you measure the total energy using using the static killing field that's present in the space-time, you measure that the total energy in the box is decreasing by the redshift factor as you're lowering it towards a black hole. You're extracting work. At a fixed proper distance from the box, a distance that will be determined by a constraint I'll tell you about in a moment, hold the box stationary, where that means at a fixed proper distance according to the static killing field, according to the measure fixed by the static killing field from the event horizon. Quasi-statically draw the piston back a little more, lowering the temperature of the fluid, keeping entropy unchanged, lowering the total energy by the work done, and the value of the final temperature is fixed so that the change in the total entropy vanishes during the entire cycle. Finally, quasi-statically eject the fluid falls into the black hole, delivering mass energy as heat and positive entropy. The piston returns to its initial state. You pull the box back to infinity. It takes no work because we're assuming the box and the rope are massless, as you always do in these kinds of things. And so you've completed a cycle in which you have turned the heat from the fluid inside the box into work back at infinity, and you can go through the standard calculation of the efficiency of this process. And one has to make the following assumptions. You assume conservation of energy, the generalized first law. You have to assume that ordinary entropy and entropy attributed to the black hole, if the black hole has an entropy, are additive. And you have to assume that the process can consistently be made isentropic. If you do, then it turns out that the surface gravity plays the role of integrating factor for heat dumped into the black hole. So kappa really is a physical temperature. And you can show that the systems equilibrate and the cycle will be isentropic exactly when the temperature of the fluid is the same as the temperature of the black hole, corrected for by the Tolman redshift factor. And it actually, very nicely and quite unexpectedly, at least to me, a very, very simple development of the argument actually shows that there must exist a universal constant, alpha, that characterizes this kind of thermodynamical process, or that's begging the question, this kind of cycle for black holes, and that universal constant actually has the correct physical dimension, mass squared, so that you can, in fact, in the purely classical regime, normalize surface gravity and area to have the proper physical dimension of mass and, of temperature and entropy. So I'll conclude with just remarking on one more thing. In order to make all this work, of course, one has to have an idea of what one means by quantity of heat transferred in a process. And there are arguments that, for instance, Bob Wald makes, but I think are right, that if one is going to define a quantity that one can reasonably think of as quantity of gravitational heat exchanged in such a process, it's going to be the change in the total mass of the black hole minus the change in the irreducible mass. And I can give you arguments for why that's a reasonable definition. I also just mentioned two more things that go along with this work that support the idea that classical black holes have a good thermodynamical theory. Because thermodynamics, let's face it, is a lot more than just the four laws. You have transitivity of equilibrium, you have the phase space of equilibrium states and quasi-station, and the distinction between reversible and irreversible and quasi-stationary and quasi-static and adiabatic transformations. You have the relationships between the various thermodynamical potentials and intrinsic and extrinsic physical quantities. There's an enormous amount to thermodynamics that isn't encoded just in the four laws. And one of the questions I'm interested in is, how much of the rest of thermodynamics can one recover? And I actually claim quite a lot. And a lot of what you can recover is in fact encoded in what I claim, given the definitions I use, are the appropriate analogs or translations of the Clausius postulate and the Kelvin postulate for black holes. So I'll leave it up there. I won't read them. You can read them. But I will just say that I don't have a proof of the Clausius postulate, but I actually do have a proof of the Kelvin postulate. It's based on the same methods that Wald and Gao used to prove their physical process version of their first and second laws. And one can use that, it's actually a very simple extension of their arguments to prove this. So the fact that one not only has the 4 laws, but one also has what in classical thermodynamics are very often considered as the foundation of the 4 laws, at least the Kelvin postulate, if not the Clausius postulate, I think says quite a lot about, I think it's very strongly suggestive that classical black holes are perhaps more thermodynamical than standard orthodoxy and folklore has it. Thank you.
So we have time for some questions and thoughts. Yes, please, David.
I'm just trying to see how this would work in full. So suppose it is the case that classical black holes count as fully thermodynamic. So it ought to be possible, if that's the case, for me to be able to take some non-gravitational thermodynamic system that's at a lower temperature than some given black hole and put them in thermal contact by whatever the means is supposed to be of putting them in thermal contact, and let the black hole be Schwarzschild. Right. And then what's supposed to happen, if this thing is thermodynamic in the fullest sense, is that I have an energy transfer out of the black hole to the thermal system. So the ADM mass of the black hole, which is the thing in the first law that's standing in for energy, is going to go down. But if that happens, then the surface area of the black hole is going to go down, and that seems to violate the area theorem.
So that very good. It is so. Here's a great example of what one might think of as if I think what I'm saying is going to capture the problem you're pointing at. I have a Schwarzschild black hole. It has a certain temperature, and I have a box full of fluid at a given temperature that's lower than the surface gravity, than the temperature as determined by surface gravity, and I just throw it in. That seems to be a spontaneous transfer of heat from a colder body to a hotter body. Is that the kind of thing that you're worried about?
It needn't be. I'm abstracting away what the thermal contact mechanism is. Just let there be my non-gravitational, or gravitation, if you like, system. Right. Let there be heat flow by whatever means heat flow is supposed to proceed by. Mm-hmm. And at the end of that process, then the mass of the black hole has gone down. And again, that can't happen because of the area theorem.
No, that's not right. Because first of all, Schwarzschild black holes have negative heat capacity. So, for instance, if you have two distant Schwarzschild black holes, say, that are so far away that they're only very weakly gravitationally coupled, but still close enough that, let's say, they're in a very, very large orbit, so there's gravitational radiation that's being given off by each, and in some sense being emitted and absorbed by each. In principle, I claim what should happen is that if they can remain in stable orbit for long enough, they will eventually, in fact, both of their masses will eventually increase until they are the same, but one will just increase more quickly than the other. So giving off gravitational radiation does not make black holes lose ADM mass.
Yeah, I don't think I buy that, but I think let's take it offline.
Sure.
So you mentioned that when the box is lowered toward the black hole, that the observer inside the box wouldn't notice anything, but of course he would, because eventually there would be a strong gradient acceleration across the box, and work would be done on the fluid and compressing it and so on. Does that have any relevance to your theory?
In one sense, you're exactly right. Of course, the person in the box, being lowered in the box, is going to notice that he or she is, being stuck more firmly to the bottom of the box as the box is getting closer to the black hole. When I said nothing changed, I mean nothing thermodynamically changes. If that person in the box is making measurements of temperature and entropy, he or she won't see anything change. That assumes, of course, that the box is small enough that you can ignore the redshift gradient, because otherwise you'd have to take into account the Tolman factor.
Yeah, so if you're right, does that mean that there's a classical statistical mechanical underlying theory that's going on underneath GR?
Purely classical, I don't know, but that's in fact what my hope would be, is that one could at least, so in the same way that one can give, we all know atoms and molecules are really quantum mechanical. And yet there's a beautiful theory of the statistical mechanics of the air in this room that is purely classical. So one might hope, and of course the story there is going to go something like the following, where, well, atoms and molecules are purely classical are really quantum. But in the regime that we're dealing with, and given the approximations we're making and the uses that we're making, the uses that we're putting the statistical averaging techniques to, we can safely ignore the known quantum mechanical properties. So presumably there's some underlying quantum theory that will give the true statistical accounting, and yet, at least in some regimes, certainly not in all regimes, because ordinary thermodynamics doesn't work in all regimes, but in some regimes, one will be able to, if one knew the full quantum mechanical underlying statistical theory, one could in fact transform it into a purely classical statistical theory of, I don't know, little atoms of curvature or something. Along the lines of something like Padmanabhan has in mind, although I don't want to attribute this view to Padmanabhan. But there could in principle be, I don't see any reason why not. There could be an intermediary statistical theory between an underlying quantum theory and the thermodynamical equation of state that Jacobson would have it of the Einstein field equation.
But wouldn't that be the theory you'd want to quantize, not GR?
Exactly. If that were right, then if that were right, then that would seem to be very strong evidence for something like Jacobson's point of view. That's the theory you should be quantizing, not GR. He just doesn't believe it so much, he's not going to bother.
So, Erik, I got a little bit lost in the Carnot-Garrosh cycle that you described.
I went through
so I'm going to ask you a very kind of a pointed question.
Please.
So let's say I've got a black hole with the temperature T, and I'm going to do what you said. I'm going to lower a box, and let's say my box is full of radiation. That's the contents. And I do two experiments, one in which my box starts with radiation that's hotter than the black hole, and the second experiment when it's colder. So could you kind of run through the Garrosh cycle?
Yeah.
How would the two cases differ?
Yes. In effect, the only difference is at this stage, where at stage 4. So I was assuming that you were starting out with the fluid hotter. And at this stage, so you lower the temperature by drawing the piston back even a little bit more. But in the case where you start out with the fluid being lower, then you would quasi-statically push in the piston to raise the temperature. And
that work of either sign is coming from infinity? Is that the way I should look at it?
That's right.
And that's the counting that you take care of too?
That's exactly right.
Okay, thanks.
Since you told us at the beginning we were going to disagree with everything you said, I was feeling disappointed because you weren't saying anything I could find to disagree with.
Oh, crap.
But then you succeeded in your answer to one of the questions.
Excellent.
So suppose about if there could be a classical statistical system underlying. So suppose we throw out everything Hawking did, which you said you wanted to on the third. But then there's also Bekenstein's arguments, right? So Bekenstein already had the area. And if the entropy is proportional to the area, just dimensional analysis, you need an H-bar. So how can you ever have a classical statistical system that gives an entropy with a, it's not like a gas of photons where it's a log H-bar, it's a 1.
Right. So in fact, I mentioned that one gets, in fact, that there's a very simple dimensional-based argument that follows from the calculation of the efficiency and the construction of the absolute temperature scale for this, what I'm calling the Carnot-Garrosh cycle. And there's just a very, very simple argument that follows. I knew someone might ask this. I actually went ahead and have the argument for the derivation of the universal constant, in case you're curious to see it. That shows that for this kind of process, you do in fact, the universal constant of the proper dimension just falls out. Now, of course, we're all going to say, and I fully believe, at bottom, this constant is just h bar disguised. It's h bar dressed up, and ready to go town in the classical world. But that's not a problem, because of course the world is at bottom quantum. But if I'm right, it's quite remarkable that already in the classical world, h bar is making itself felt in a way that you don't need a quantum mechanical analysis to derive. But the same thing, I claim the same thing. So the same thing happened with Boltzmann's constant.
So you just want to say there's another fundamental constant of nature
It's
with
not-
the same dimensions that is not h bar.
It's not. It's not. My very strong guess is, if this is right, then of course it's some factor or multiple of h bar. But there's just no way of knowing that at the class. Secretly between you and me, it's some factor of h bar. But
of course,
you
that's
don't
the
know
beautiful
that
thing
conditional.
about it, that you start
Yeah.
doing classical
And all of a sudden,
physics and you're
yeah.
led to quantum.
I think that's
Yeah.
exactly right. Yeah.
Yeah. Okay, you failed to say anything I disagree with.
Damn.
Thank you, Erik.
This is one of these placeholder titles you give when somebody asks you to give a talk and you, at the time of giving the title, have no idea in detail what you're going to talk about. So here's a corrected title that fills in, that is consistent with the original title, but fills in some more of the details. So there's bits of philosophy philosophy of physics, which are sort of closer to philosophy of science. This philosophy of physics is going to be much more on the physics side. I'm sort of going to take advantage of the philosopher's prerogative to give a sort of physicsy talk that's long on conceptual questions and diagrams and short on concrete calculations. In my defense, this is talk 31, so I suspect you're quite keen to the number of calculations to be kept under control at this point. Okay, so I just want to review very quickly what the shape of the history of black hole thermodynamics has been, particularly quickly since Erik's already done the first part of it for me. So here's the lightning history as it's normally told, and I'm not particularly going to challenge this way of telling it. So we start by thinking there's at least a formal analogy, and we see that through classical thermodynamics, through results about stability and equilibration, through results about the black hole laws of thermodynamics. We then start saying, okay, are these things thermodynamical systems in the fullest sense? And the derivation of Hawking radiation, and the various arguments for the Bekenstein bound in quantum field theory that underpin the generalized second law give us reason to think that black holes seem to be behaving thermodynamically in the fullest sense, and so as long as we're thinking in terms of thermodynamics as a sort of phenomenological large-scale theory, then black holes seem to fit into it perfectly well. So it becomes super tempting to say, well, look, all of the other thermodynamical systems we see in nature, we think we've got an underlying understanding of their thermodynamic behavior that comes back to their statistical mechanical properties. So, hey, maybe black holes are statistical mechanical systems as well. And we make sort of various steps towards that. We can do, Gibbons and Hawking did saddle point calculations, started getting out the standard black hole entropy from a sort of low energy quantum gravity, if you like. Whole bunch of different results, qualitative, sometimes quantitative, in various approaches to quantum gravity, in particular in string theory, seem to get both the mathematical form of the entropy and a bunch of the details of the entropy. And the ADS-CFT correspondence, in particular, strongly seems to suggest, insofar as it's right, that the description of a black hole's thermodynamics, and in particular its radiation, is dual to a description that's quantum mechanical and in the fullest sense, and can be handled in standard sort of unitary quantum physics without any funny goings-on. So that there is a very strong sense there that a black hole, as one of the speakers yesterday said, is just like a cup of tea. It's just a thermal system. Its radiation is just thermal in that sense. A lot of that can be challenged in various respects. I'm not going to challenge it for this talk. I want to take it as read and just explore a small puzzle that comes from that. So I'm going to assume as a background something that's assumed fairly standardly in at least a big chunk of the sort of quantum black hole literature. I'm going to assume a paradigm where I can think about my black hole as a thermal system as lying on a membrane that's just outside the Schwarzschild radius of the black hole. So I imagine I've got a surface just outside the the black hole with an area just maybe 1 Planck unit larger than the area of the event horizon. And we're going to assume that that system is just an ordinary quantum system. It's got quantum degrees of freedom, it's hot, and the black hole radiation is ordinary thermal radiation on that stretched horizon. And if it is an ordinary quantum mechanical system, then at late times we're going to see deviations from the prediction of semi-classical prediction of the Hawking radiation. We're going to see that the late time radiation is quantum mechanically entangled with the early time radiation, just like in thermal cooling, so that the whole evolution process carries on being unitary. So your sort of thought experiment here is I start with some chunk of matter which, just for convenience, we imagine is in a pure state. We let it collapse to a black hole. The black hole eventually evaporates away. That whole process is unitary, so right at the end of the process, all of the radiation coming out of the black hole must be collectively in a pure state. If the Hawking derivation gets the phenomena right at a given window of time, then the individual photons coming out in the radiation are in mixed states, but those mixed states have got to be entangled in some way so that we recover the original quantum pure state from the infalling radiation. Again, you can challenge this. Again, I'm just taking that paradigm as read for the purposes of this talk. And I think it's nice to see that if you look into the sort of details of how the Hawking radiation structure works, you get sort of pictures that look a bit like this. So if you just look at the radiation with respect to the killing time outside the horizon, you find that you get this kind of qualitative story. You find that for the bulk of the radiation, which has pretty high angular momentum relative to 1, you find there's a potential barrier due to the angular momentum barrier and the Schwarzschild potential. So you find you've got a sort of bath of equilibrium radiation sitting trapped between the stretched horizon and the potential barrier. So you go towards the stretched horizon, then your confidence in semi-classical physics gets more and more uncomfortable, and as you start getting close to that horizon, you can start to expect sort of Planck scale physics to take over. The other side, you expect on the far side of the barrier the radiation to be leaking out and to be seen at infinity as blackbody radiation. So it's got the sort of shape of an ordinary thermal system with a core and an atmosphere, and with rather like a gas giant or something, I guess, with a rather blurry boundary between the core and the atmosphere. So it's all kind of, I think, quite an attractive picture. Where it gets us into puzzles is thinking about the interior of the black hole on this setup. So if you sketch here's a Penrose diagram, a conformal diagram for what black hole collapse ought to look like on this kind of story. So I have my shell of incoming matter coming in, that's the blue line on the left. I have a dotted line that forms a horizon. I've got the red arrows of the Hawking radiation coming out. If you work in a Heisenberg version of quantum mechanics, so the quantum state doesn't change, the observables change, then if the infalling matter has quantum state psi, then the outgoing radiation at late time, it also better have quantum state psi, just because it's unitary. And it also looks like because nothing particular has happened to it, the infalling matter also has quantum state psi. And if you look on the sort of green surface there, sort of quite late in the period before the black hole finally evaporates, it looks like that surface contains both copies of psi, and that looks in contradiction of unitarity. We know that in quantum mechanics you can't clone a copy of the quantum system. So for a while, and to some extent still now, there was an answer to this, a standard response, which goes by the name of black hole complementarity. And this links to some of the discussions yesterday again. We say that, contrary to what we might think using semi-classical methods, the quantum description of the interior of the black hole isn't in addition to the exterior, it's a redescription of the exterior degrees of freedom, or it's dual to the exterior degrees of freedom. So somehow we think that the interior goings-on are a redescription of what's going on in the quantum mechanics of the surface, or perhaps the exterior more broadly. The most obvious interpretation there is just to say, well, those degrees of freedom on the stretched horizon are to be reinterpretable as degrees of freedom inside. And you can see this is another version of the holographic ideas that came up yesterday, only here applied to the boundary of the black hole rather than to a conformal boundary at infinity. And a lot of the sort of more conceptual bits of the discussion of black hole thermodynamics got roiled a few years ago when AMPS pointed out that in a bunch of thought experiments that it seems to be the case that you could arrange for a single observer somehow to interact both with the exterior radiation and with the interior of the black hole by waiting long enough after the black hole was formed to jump in. I'm not going to, for reasons of time, I'm not going to explore how that argument works or whether it works. What I'm interested in here is the solution to the problem that AMPS posed. They said, okay, well, suppose that the following would solve the problem. Again, the wrong way. Suppose that change your conformal diagram. Suppose that the agent falling into the black hole at late times at least, or matter falling into the black hole at late times, doesn't encounter the smooth surface you might expect. They actually encounter just a tremendous amount of energy at the Planck scale, and basically that's enough to wipe away the information in the infalling radiation, or wipe away the pesky observer who's planning to spoil the experiment. As a kind of ad hoc feeling to it, it certainly prevents the paradox. It's arguably a natural consequence of the idea that all of the entanglement now is between early and late stage radiation, so that the exterior of the black hole is not entangled anyway with the interior. If you take a boundary across space and you disentangle the quantum fields on both sides of the boundary, you get a ton of energy at the boundary. And there's also some evidence that, for what it's worth, that in the ADS-CFT correspondence, that firewalls are, in some sense, generic or typical, although that argument has less of the sort of operational flavor. So again, I don't want to push too far into what the alternatives people had to this. I want to look at a quite modest question here. This is where my interest as a philosopher comes in. Why not firewalls? What's the reason, other than weirdness, not to think that there should be a point at the horizon, either where there's so much energy that anything coming through gets sort of leaked to its information, or there's so much energy that the low energy space-time description just breaks down. And I think there are two obvious arguments you come up with. Or two obvious concerns, I guess. One of them is that it seems there's a danger it's going to undermine the original argument for Hawking radiation, and I'll say more about that in a moment. And the other, and perhaps more powerful, is just to say, well, the physics just outside the horizon seems perfectly well behaved. Horizons aren't even a local phenomenon. To make that vivid, here's a standard sort of collapse to a black hole model that gets used in the quantum gravity literature, rather than the sort of messy astrophysics of having a fermionic time-like chunk of matter undergo collapse. We just send in a thin infalling shell of radiation. So now inside the shell, space-time is Minkowskian. Outside the shell, it's Schwarzschild. You see the event horizon there is already forming in the Minkowskian bit of the space-time. So, I mean, it sort of feels bad enough for the poor observer who's inside the radiation shell and is doomed to be crushed to the singularity, without supposing that somehow they're sitting there all unsuspecting and some random sheet of Planck-level radiation appears from out of nowhere. I think that's actually a pretty good argument, and I'll come back to it. Let me say something quickly about the first argument. So I think the right way to think about why that in itself is not a huge concern is just to think of how the Hawking radiation derivation goes, and here's a sort of sketch of it. And it's easier to see this sketch if you sort of take the extended Schwarzschild space-time that happens if I just put the matter away. So on the right-hand side, I've got the exterior space-time. At the top, I've got the black hole. Below that, I've got a white hole. On the left, I've got another copy of space-time. We don't want to take that space-time seriously, except the sort of top right corner, but it's useful to clarify the quantum field theory. So to work out how to do quantum field theory on that space, I have to work out what ground state I want to use, or what state I want to put the system in, if you like. So one natural starting choice is to say, well, there's no radiation. The static observer, and particularly the observer at infinity, doesn't see any radiation. That quantum state is singular on the past and future horizons. Another choice, Unruh's choice, that in the Unruh vacuum, I can imagine I've got outgoing radiation visible at the Hawking temperature, but no incoming radiation. That state's singular on the past horizon, but it's regular on the future horizon. And my third choice is the heart of the Hawking vacuum. The static observers see outcoming and ingoing radiation at the Hawking temperature, and that's regular on both horizons. I put vacuum in quotes here because it's pretty clear a thermal state. It doesn't feel like a natural candidate for vacuum, but it's a reasonable quantum state. So the normal way one thinks about black hole radiation tends to be you start with something like the Unruh state as representing at late times. So I haven't got any radiation coming in, but I've got radiation going out. It's regular on the horizon. I want a quantum state that's regular on the horizon. It is the unruh state's irregular on the past horizon, but I don't care because the past horizon is fictitious anyway. I don't trust the space-time for the past horizon section. And then the concern is going to be, well, why did I impose the condition that the quantum state was singular on the horizon? And the natural reason would be because I need a smooth experience for the observer crossing the boundary. If there's a firewall anyway, that's pretty unpersuasive. If I'm already saying, let's suppose as soon as I cross the horizon I get annihilated by Planck level radiation, then the requirement of a non-singular vacuum seems to go away. But the thing to realize here is that the form of that, of the way in which say the Boole-Ware vacuum goes singular is not in a sort of sudden rush when it reaches the horizon. So that the length scales on which the wrong vacuum deviates from having sort of zero stress, normalized stress energy is of the order of the Schwarzschild radius. So if you were even within sort of a Schwarzschild radius or so of the black hole, or several Schwarzschild radius, you'd start seeing a significant deviation from zero stress energy. So you'd expect to see a significant back reaction. So your assumption the Schwarzschild metric was correct just looks wrong. So let me skip the quote I have here just for reasons of time. But the underlying point here is that that if you just want to hold on to the paradigm that says I'm outside the stretched horizon, I want this thing to look Schwarzschild, that's already enough to get you towards the Hawking radiation derivation without considering an agent crossing the boundary. So I think the much more interesting case here is to say is the issue of just what we just expect from the actual formation of the black hole. And I think I just want to buy that claim, but the question I was interested in as a sort of way of getting this indirectly was to say, okay, well, forming a black hole from infalling matter, particularly in the astrophysical way, is actually, in a certain sense, a very special way of forming a black hole. What I mean by that is something like the following. If I compare the entropy of a typical astrophysical precursor for a sort of solar mass scale black hole with the black hole's entropy itself, there's a difference of an enormous fraction. And since we know that the entropy in a statistical mechanical theory is a measure of the number of states, the dimension of the Hilbert space corresponding to the black hole state is the exponent of the stress energy tensor, then it looks like we'd expect only a very, very highly atypical number of black holes to be formed through astrophysical collapse. So I was interested in, okay, well, how do we think about thermally typical black holes? How do you make a thermally typical black hole? I think the recipe is something like this, by analogy to the StatMech case. Start off with just a Planck mass black hole in a Planck mass confined region. Let the temperature, the radiation around the box in this implausible space be just slightly hotter than the black hole. Let the black hole gradually, quasi-statically heat up, and therefore, supposed to be negative heat capacity cool down. Keep doing that, continuously expanding the box, continuously letting the black hole absorb more radiation, keeping the radiation around the black hole just above the black hole temperature. This will get tedious after a while. When you get bored, reverse the process, get the temperature just below the black hole temperature, keep going down, and eventually let the black hole fizzle away, and do all of this quasi-statically. Okay, so ask yourself what the space-time diagram looks like for that. Well, here's a natural thing I think you think of in the first go of it. You think, okay, it's pretty much like the ordinary collapse. I have a formation moment at the beginning, I have a stretched horizon, and I have gravitational collapse on the singularity in the usual way. This isn't plausible for a minor reason and a major reason. Minor reason is not at all clear what's going on the y-axis here, and the major reason is this is not time symmetrical. And the construction of a thermally typical black hole is a time symmetric process. So if you ask yourself what's the space-time going to look like for a time symmetric black hole, I think it's hard to avoid drawing something like this to the exterior. You have to have a time reverse, symmetric diagram here. You've got the stretched horizon going from its formation point to its final evaporation point. And if you then try to fill in the interior of that diagram, I think you get confused pretty quickly. So if you start sort of extrapolating inward, you've got you start writing a future singularity. So by symmetry, you start writing in a past singularity. So now I've got a naked singularity in my space-time, which is uncomfortable. Maybe I know what's coming out of that naked singularity into the exterior region just by Hawking's calculation, but I've got no idea at all what's coming along the horizon, which is exactly what's salient for whether there's a firewall. If I also start filling in the space-time further to the left of the diagram, again, it's completely unclear what I want to do. Unless I want to go all the way through to another universe, I seem to need to cut it off somewhere, but I don't seem to have any good motivation for doing that or any non-ad hoc rule for what it is. So when you start writing in what the space-time extrapolated into the interior looks like for a thermally typical black hole, the temptation of saying, well, you just can't do that, that isn't a consistent space-time story beyond the horizon, starts to look kind of attractive. So just to sort of conclude that tentative set of sketches, there isn't an assumption from the horizon smoothness required to get the Hawking radiation. And for the thermally typical black holes, although clearly not the astrophysical ones, it's pretty mysterious how I'd fill in the interior without the firewalls. So tentatively, I think if you think that through, it starts giving you some support for the idea that we should be interested in a theory of the black hole interior that only works or only needs to work in highly atypical cases, that we don't need a general theory of the black hole interior. Okay, I'll stop there, thank you.
Thoughts and reflections? Erik?
I just want to make sure I understand. I just want to make sure I understand. So AMPS claim that their paradox follows from the three assumptions. Nothing special at the horizon. Entanglement isn't broken by crossing the horizon, and the semi-classical approximation is valid. Quite close to the horizon, and they give up. Clearly, nothing special happens at the horizon. Sounds like you're giving up semi-classical is good. Is that correct?
I don't think so. I mean, when they say semi-classical is good, they mean semi-classical is good outside the horizon.
Yeah, but they think it holds. I mean, at least in the paper, they think it seems to hold pretty close up to the horizon, up until you're quite close to the firewall.
Yeah, sure, but that's all still outside the horizon.
Yeah.
Yeah, that's fine. I'm not giving that up.
Okay.
I should say over and above that, from the point of view of the paper here, I'm not really taking a stand on what and where is right or wrong in AMPS's framework. I'm just sort of thinking through, is there any particular reason to expect or not to expect a firewall in the first place in the thermally typical case?
So you're not taking a position on if one accepts a firewall and one accepts that the AMPS argument works. You're not taking a position on which one of the three assumptions we should give up.
Well, I mean, look, if you have all these three assumptions, you get into contradiction of firewall. So if you have all those assumptions minus a firewall, you get a firewall. That's the structure of it. So since I'm just sort of considering, well, suppose there is a firewall, the other assumptions there are free floaters.
Okay.
Yeah, AMPS's argument is a motivation for taking firewalls seriously, even though they're apparently paradoxical. I'm sort of interested in the question, well, are they such a paradoxical thing to expect anyway in the thermally typical case? I think the argument against them in the astrophysical formation case for young natural black holes sounds pretty good to me. And I don't know how one should respond to that, but that's sort of orthogonal to the issues here.
Oh, sorry, Robert Shorty had the microphone.
Okay, sorry. So your thermally typical black hole formation and evaporation, is that a unitary system?
I'm assuming so, yeah.
You're saying
That's just I'm taking that as a premise, yeah.
you're taking that as a premise, even though it's got a naked singularity.
Well, in a sense, that's part of the problem. So, where do we get to? It looks to me like the conformal diagram you have to draw for the exterior, assuming the whole process is unitary, looks like that. And the fact that when you try to work out what would you draw in the interior, you start drawing you start having to put in a naked singularity is part of what makes me feel that trying to draw in the interior in that situation starts to look suspect.
But then you're putting your firewall, and that's supposed to bring back the unitarity? Is that the idea?
Well, I mean, with the clear confession that in many respects I'm out of my depth here, my way of thinking about the firewall here is what I'm supposed to have here is a quantum theory of gravity. The idea of a quantum theory of gravity is that at low, i.e. sub-Planckian energies, I get out something that looks like classical general relativity. At high energies, I expect a breakdown of a classical space-time description altogether. So I think thinking of the firewall as sitting in space is probably not the right way to think about it. I want to think that the firewall is an ending of the period where I can actually extrapolate space. So if there's a firewall at the stretched horizon, or just within the stretched horizon, then I'm just not legitimated in extrapolating space beyond that. That's how I'd imagine understanding it.
Okay, I'm just concerned because it's 5:23 and we wanted to end at 5:30. So maybe Avi and I just very briefly together, the first one and then the other, and then just respond.
So very quickly, we know of one place where there is a pathology, and that's the singularity. So why are you thinking of the catastrophe as happening in a completely new entity called the firewall rather than near the singularity somehow?
Well, largely in this case, because it would have to be, I'll give it as a quick answer, because it's a past singularity, and because I don't really know how to extrapolate the space-time in a non-arbitrary way in the leftward diagram, space on the diagram either.
Andrea?
So the conclusion that effective field theory breaks down at the horizon was suggested in order to get unitary black hole evolution for somebody who collects the Hawking quanta coming out of the black hole. And so you needed this exact entanglement between the interior modes and the exterior modes. So in infalling, if you now conclude that there's a firewall at the horizon, you basically say effective field theory breaks down. And then when you let an infalling observer cross the horizon, since effective field theory breaks down, one should perhaps try to find the underlying theory that goes beyond effective field theory. And if you do that, there is the possibility that because the infalling observer has only a finite amount of time to fly through the horizon of the firewall, that there is an approximate sense of how space-time can emerge because you don't need this exact entanglement for the infalling observer.
Yeah.
Because the argument was based on effective field theory, and the conclusion was effective field theory breaks down, and so one should go beyond effective field theory to try to understand what's going on.
Sure. If that's a comment, I'll just let the comment stand for reasons of time. Thank you.
Thank you, David.
Okay, so my name is Jeroen van Dongen. I'm a historian and philosopher of science, and I will be talking about the history and philosophy of the black hole information paradox. And the title is chosen because I'm going to give a history of the black hole information paradox and argue that that may teach us something about how, philosophically we can understand science. So this is some of the questions that I'll be addressing. Why is a black hole a central object in theoretical study? And then, of course, particularly in the context of the black hole information paradox. How have theorists interacted with the black hole and with one another? And perhaps most importantly, what does that tell us about how science works? And this is what one of the main participants in the black hole information paradox had to say about that particular question. Generally, like most physicists, this is Leonard Susskind, generally like most physicists, I'm not very interested when philosophers opine about how science works. So I understand I come to you, at a bit of a disadvantage, but please bear with me, and also, let's follow Suskind's advice, who was reading on, and read on what he says, namely, shortly before the Santa Barbara conference on black holes, this is in 1993, I had read Thomas Kuhn's book, The Structure of Scientific Revolutions, and Kuhn's ideas seemed right on target. They managed to put into focus my own fuzzy thoughts about the way physics had advanced in the past, and more to the point, how I hoped it was progressing in 1993. I felt that the black hole war was a classic struggle for a new paradigm. And, Kuhn will resurface in this talk, actually some of the ideas of our chairman today, who I happen to believe is one of the most important historians, or perhaps even the most important historian of science since Kuhn, will also focus in sort of trying to, will feature in how we actually can understand this debate that evolved in the 1990s and beyond, and before, of course. So, why is a black hole a central object of study in theoretical physics? is of course the key solution to the general theory of relativity, but it produces all these conflicts. It produces conflicts with theories of quantum field theory. It produces conflict with thermodynamics. And of course, if you have these points of conflict, that's where new science might appear. So clearly, if you're interested in producing new theoretical physics, you're going to look at these points of conflict. And indeed, the black hole has served in that manner. Oh, I'm sorry, my thing seems to be, maybe I should actually, oh, okay. So this diagram is a diagram that in history of science, we've seen before. This is exactly the same kind of diagram you can draw for Einstein in 1905. And then in the case of Einstein, you would have mechanics, thermodynamics, and electrodynamics as the three main theories. And then you again see these points of conflict, and then you can ask the question, well, how does Einstein try and address these, right? What Einstein does initially, which ended up not in his publications, is that he came up with some sort of constructive attempt to, in one go, with some proto-atomistic theory, in one go solve all these problems that he had, and then failed. Didn't publish this. This was some sort of proto-atomic theory, and then retracted from that position, formulated a bunch of principles, and kind of reasoned on the basis of these principles. We see kind of a similar motion in the work of some of the physicists that I'll be talking about. Now, these equations, we've seen today and yesterday, of course, many times, and I'm sure you're very familiar with them. Laws of black hole mechanics, published 1973, also in early publications. Indeed, formulated as analogies, right? And then, of course, Jacob Bekenstein, he proposes to interpret the area, actually not just look at an analogy, but actually interpret this thing as an entropy. However, he actually, in his original publication, distinguishes this from a thermodynamic entropy. He believes that it's, an entropy above and beyond the thermodynamic entropy that you actually need to make the second law consistent. That's one sort of tradition that feeds into this study. Another tradition is the study of quantum field theory in curved spaces. There were already some results here. This is studied in the context of cosmology particularly. And Stephen Hawking combines these two developments into his own result that black holes evaporate. Right, and in the analysis, you have a vacuum state sort of in one coordinate system. You look at that very same quantum field in another coordinate system. You see a mixing of creation and annihilation operators. And in the second coordinate system, the outside observer's coordinate system, you see a bunch of particles emanating from the black hole. So this is, of course, Hawking radiation. Now, fairly quickly afterwards, Stephen Hawking produced an argument that suggested that information is lost in the evaporation of black holes. David has already, mentioned how this works, and again, many of you will be very familiar with this story. There's a quantum state that sort of evolves. Part of the quantum state ends up behind the black hole horizon. Nothing can come out of the black hole horizon. So, therefore, in future infinity, you're going to end up with a mixed state because, this quantum information cannot escape from behind the black hole horizon. And this interpretation is particularly sort of safeguarded by the idea that you do have this vacuum state in an infalling coordinate system. So, an infalling observer can, in fact, pass the black hole horizon. He doesn't, in fact, see these particles, right? So these two ideas are, or these two ways of looking at the black hole, in that sense, are also consistent with the notion of information being lost and the principle of equivalence, one could say. So when studying this problem as an historian, I have done a bunch of interviews. Some of these are more recent. But in fact, I actually started doing this in the 1990s. I was a physics student in Amsterdam. And if you are a notable physicist who was studying the black hole information paradox in that period, you may have been interviewed by me. I was then also making extra money as a science writer with a keen interest in the information paradox. So, maybe there's all kinds of compromising material in my recordings that will yet surface. I haven't mined that material just yet. But a bunch of quotes are going to be featuring here, and they sort of give us a bit of a sense for how people relate to this debate. So Bob Watt, for instance, said, when I first heard of Hawking's information loss result, I thought, wow, that's very neat. Just not controversial in any possible way, and in fact, in the community of relativists, this was something that was, seen positively. Gerard het Hoofd, who will become one of the main spokespeople against the interpretation of Hawking, says that essentially in his community, which is particle physics, this result was kind of not seen. If you do a bit of citation analysis, what you see is that, the result was accepted in relativity, and if it did surface, I am afraid this may happen on more than one occasion because this thing is kind of loose. Maybe I'll just keep talking. Yeah, if you do a bit of citation analysis, what you see if this result, information loss, is cited in the field theory community, then again, it's not really particularly controversial. It's just seen as a result in relativity theory. So het Hoofd is a clear example of somebody starting off in a constructive manner, moving on to a principled manner. However, unlike in the case of Einstein, he actually doesn't, get what he sets out to do. He doesn't actually get, a full theory deduced from his principles and assumptions. This is how he starts off being interested in quantum gravity. He does other things at the same time, but this is one of his ideas. You have, some grid of space-time points. You define some quantum states on this, and perhaps somehow you can construct some sort of a quantum space-time on the basis of this. Clearly very constructive, clearly sort of bottom up, you could say. Were there any discussions on these ideas, on the information paradox? Not really. Bill Unruh, another person I spoke to, says, well, separate fields. Particle physicists didn't seem particularly interested in gravity to begin with. And Gerard het Hoofd observed that, when he approached people that were interested in quantum gravity, which mostly came from the relativity side, they kind of felt uncomfortable with the way that he treated, for instance, typically relativistic objects, like, for instance, the metric, right? He says, relativists protested the way that I treated the metric. The metric was absolutely sacrosanct. And het Hoofd sort of makes this interesting point, and this also clearly connects to some of Peter's ideas. He points out that it was difficult to communicate, that people didn't share a language in which to express, their ideas, that this made it, difficult to understand one another. And this is something that recurs a number of times. So then in the 80s, people start being interested. To Bill Unruh, this was a surprise. This came out of nowhere. My initial instinct was that the sort of the game changer in raising this interest was a kind of axiomatic paper that Stephen Hawking wrote in 1982. He sort of sets out a bunch of principles that any future quantum gravity theory needs to adhere to. And one of these principles is non-unitarity. And I thought, okay, well, clearly this is so offensive to particle physicists, they feel like they need to step in. But in fact, that's not really what happened. Susskind has a recollection that he went to some meeting where for the first time he heard Hawking's ideas, and it kind of stuck with him. He believes that het Hoofd was at the same meeting. Het Hoofd himself claims that there was a different meeting, but basically it was a more informal experience. So het Hoofd at this point says, look, I just was sure that a black hole is just nothing but a normal thing, a normal thermodynamic object that we have seen on many times before. Wow, okay. So het Hoofd starts doing this principled approach. He assumes an S matrix and then tries to see what he can derive on the basis of this. Susskind has an argument against non-unitary evolution. This principled way of thinking then brings het Hoofd to the holographic idea, which then eventually starts working indeed as a creative principle. Susskind believes that there wasn't too much of a debate, and both he and het Hoofd were very much, this is the 1980s, were very much dissatisfied with the situation. The relativists were not convinced by the arguments, or they couldn't actually follow it. Right, so Unruh says, he couldn't follow the articles that Gerard het Hoofd was writing. He just, didn't understand them. And in fact, in 2012, I was told that, there was also no real cross-communication. Now, lately, Bob Wald told me that that's no longer the case. That, particularly in the case of the firewall debate, he feels like, there is, in fact, communication across fields. So then the debate sort of accelerates. This is partly due to work that also Professor Strominger produced on a 1 + 1 dimensional black hole. There the information paradox was expected not to arise. Interestingly, Bill Unruh says that he just, again saw this development taking place out of nowhere, right? That he didn't follow that literature. He just, to his surprise, suddenly people were really interested in the information paradox. And het Hoofd sees these developments also as not entirely satisfying because they just started doing things that he disagreed with. And then he's speaking about string theorists in particular. The idea of black hole complementarity is floated, and this then starts sort of bringing on people on the field theorist point of view. But one couldn't actually do calculations, but that changes with the introduction of the D-brane. And then Professor Strominger with his colleague here at Harvard, Kumun Vafa, they actually do a calculation of the black hole entropy. And this then is the sort of the main game changer in terms of, you know, the unitary perspective becoming the received view. Many more people start pouring into the field because there are now calculations one can do. And then on top of that, very quickly afterwards, ADS-CFT gets proposed, which you know, suggests that there's a gravity theory which you can map onto a field theory, and therefore whatever happens in gravity should be also describable by a unitary field theory, therefore information should not be lost. And in the words of Leonard Susskind, I knew the black hole war was finished when that result was published. Okay, so yes, many more people start pouring into the field. The number kind of shifts in the way that, you know, people now believe, or the majority believes, the new paradigm, so to speak, arrives in which information is not lost in black hole evaporation. Now, you know, if you take a bit of a step back and kind of look at what happens here, some things stand out. This must have been a pretty emotional debate. If you look at the way that Susskind writes about this, right? Like, he's talking about a black hole war, a battle with Stephen Hawking, neutrals turning into allies, you know, this is martial language, and he's, you know, emotionally engaged. High stakes, clash of principles, and these principles get written in capital letters, right? So there's, you know, this is a big deal. People express themselves in a very certain fashion, right? They're sure of themselves, even though, you know, there is no actual deductive certainty, right? This is not math theorems we're talking about. This is really much more intuitive. So the language of Kuhn is actually used by Leonard Susskind. In a way, he sort of portrays, you know, in 2008, the consensus as the higher paradigm. That may not necessarily be literally the way that Kuhn intended it. But still, one of the main achievements of the effort of string theorists is that now holography is what he calls normal science, right? So it's just, you know, that's the way that we look at things, right? This is the way that we now work. A bit dismissive in terms of how Stephen Hawking ended up looking at this problem. Hawking had become a tragic figure, in fact, he writes, who just didn't get the point. Okay, so, you know, how do you understand where this sort of emotion and this dynamic comes from? You have to look, of course, at people's background. So Leonard Susskind points out that Hawking was too classically wired. He was, you know, of course, a greatly successful relativist. Geert het Hoofd says sort of similar things. Hawking works rather abstractly, Euclidean gravity, so on and so forth. I like concrete things, particles, right? Like abstract stuff, of course, is not so good. Particles, concrete stuff, that's, you know, that's real physics, right? So you know, the way that I do physics is really the right way to do physics, because that's the concrete stuff, not the faraway abstract stuff. So, in a way, what you see develop here is a problem of authority. People deny one another the authority to speak about the black hole. And that's, of course, where a lot of frustration builds up, and that's why people felt so very emotional about this whole thing. But what? Most particle physicists are not used to non-Cauchy type evolution laws because they have always worked in flat space-time. They do not start with a space-time point of view, but it's awfully difficult to understand a black hole if you do not have a space-time point of view. If you're not a relativist, if you do not have a space-time point of view, do you really understand a black hole? Bill Unruh, particle physicists' training is strongly rooted in flat space-time. No singularities, issues with causality. Unitarity was hammered into them by their professors so that they stopped thinking about it. Their thought processes are really all stuck down there in flat space-time, right? Like if, you know, if that's how people feel about the, you know, person you're debating with, then, you know, this is, yeah, then, you know, instead of exchanging arguments, you start raising the volume, perhaps. Okay, so, the consensus, if you would do a poll, I would think that, you know, those that think about the information paradox would kind of, you know, the numbers will be on the field theory side. Of course, the firewall debate has, you know, reopened expectations. But what you see there is that people really want to save the unitary way of looking at things, right? Because of the main achievements that ADS-CFT is credited with. But these two relativists, they're not, you know, they're just not convinced. Why not? Because they can't really follow the argument. They, you know, they can't reconstruct for themselves. They just lack the practice and training in string theory to do so. Hawking, of course, changed his mind. This was not too much regarded, regarded into necessarily positive a light. But as a matter of fact, Hawking comes across as kind of a bit of a hero in the story, because he's actually somebody who, informs himself truly about the other side's opinion and kind of retrains himself in the methods and perspectives of the persons that he's engaged with. And of course, when you do that, then you become somebody who kind of integrates into this other field and become able to, in fact, change your mind. Okay, so this story can be phrased as a Kuhnian paradigm shift, but there are also complaints you can make about this, right? There's like, I don't see necessarily Gestalt switches. Peter has also pointed out that, in Kuhn's analysis, there's this sort of wholesale change of paradigm, everything changed in one go. Clearly there are many continuities across the debate. Obviously, there are examples of people trying to find a common language, and the fact that, some feel that they haven't achieved this partly explains why the debate, ended up not being resolved according to some. You can even look at these blobs that I drew earlier. These blobs. They're theories, but they're also groups of people, right? There are groups of people that, are trained in these theories, that work in these theories, that, adhere to the principles of these theories, right? And that, that identify with the principles of these theories. So the conflict in principle also becomes a conflict between people. Excuse me. So, having said that, well, what you see here then is a clash of principles, but a clash of principles is closely tied to ways of working. And the way that you work is also tied to, of course, who you are. So, what you see here is, in a way, also people sort of weighing principles as if they weigh values, as if, the way that they approach a decision to be made between theories is something where, you don't actually have deductive certainty, but where, you ask yourself what's really important, and take that as something on which you act. Now, to come back to this bigger question I raised at the beginning, what does this tell us about scientific rationality? There is actually a bit of a debate about string theory, if that's the proper way to do science. And one philosopher of science has recently said that yes. And the argument he has that, we just see physicists do a lot of non-empirical theory assessment. And given that that's the case, we should broaden our horizon and sort of move to a position where we also allow sort of theory assessment to take place on the basis of theory alone. And some string theorists have embraced that point of view, and here we're being licensed by a actual philosopher. And there's been a response to this point of view, and the response has been voiced in a very visible Nature article. I'm sure you've seen it, in which it says, no, this is definitely not the way that we need to go. We need to sort of, make very clear what proper science is. And there was this other philosopher who very eloquently expressed what proper science is. That was Karl Popper, and Popper said, well, you need to come up with a falsifiable hypothesis, and once you're in that game, then you're really doing science. And if whatever intellectual game you're involved in, if it doesn't produce any falsifiable statements, then that's just not science. The problem with that analysis, the problem with that move is, in my opinion, the same problem that drove the first move by the philosopher I pointed out. It's just, it derives upon a mistaken understanding of how science, in fact, progresses. Science, if you look at the history of science, science just works in a different manner. We don't have these isolated hypotheses and clear separations between theory and experiment on the basis of which, you can vote up or down a particular theory. It's a much more sort of human process, so to speak, and therefore I would argue that we should look at history of science at least as much as philosophy of science. Thank you.
Thank you, Jeroen. Lydia?
So very interesting, but I noticed you did mention this idea of languages being different as well when you were talking about sort of the history.
Yeah.
Right. And I wondered whether you had sort of tried to map this rather than about values, but with sort of this really nice idea that Peter has of trading zones.
Yeah.
So have we kind of, would you see this as the particle physicists, string theorists have sort of entered a trading zone where they now have started to share language,
in a way,
as well as maybe capitulate to each other's values, maybe not, completely adopt each other's values, but at least recognize them?
It's an intricate process in which a common language needs to be found and a sense of seeing what the other person's values are. And in some instances that works out, in some instances it doesn't. I don't know if that answers your question, but.
No, I was trying to see whether you see values as being distinct from language. Because one is about tools, right? I mean, it's literally the classical trading.
Yeah, no. So tools are taught in training, and I assume I'm sure you also teach at a university. I think what we do when we teach at universities is, we teach tools, but much more importantly, we teach values, and these values are much more implicit, and they're much more we're less aware of it because we focus on the tools. But the whole reason why there's such a thing as a research university is that we seem to be able to kind of form these people that have these values beyond the tools. So it's part of the same dynamic.
So this is just a slight worry, I suppose, about some of the interpretation of Susskind. I mean, the overall narrative seemed extremely plausible to me, but the worry goes something like this. I mean, from memory, Suskind's 2008 book was titled "The Black Hole Wars: My Battle with Stephen Hawking to Make the World Safe for Quantum Mechanics," or something like that.
Yeah.
And it did quite well, as popular science does. If it had been titled "Some Developments in Quantum Gravity 1990 to 2008," I think it's plausible that Susskind would have sold a lot fewer copies.
Of course.
And I worry whether Susskind had a clear motive to jazz up the conflict, particularly with Hawking as an obvious
He is an
figure.
excellent author, and I'm sure that he had wanted to sell that book very many times. That's of course part of it. But this sort of emotional aspect is not just something that you see in the title of that book. It's clear. I even remember this being a physics student myself in the 90s. Kind of, having an interest in this subject, speaking to people, this is something people felt very deeply about. So the Susskind title and his language is kind of an expression of that sentiment. And yes, I mean, some correction should perhaps be made for the incentive to sell books, but yeah.
Of course, names matter. If this was called the Totally Collapsed Object Initiative, it might have.
Yes.
Yeah, I hearing a history of a subject that I've been involved in, I can't resist.
Of course.
Commenting, of course. I think it's true that there was a time around 2000 when a number of people, probably Susskind most notably among them, were claiming that the problem had been solved. And I think in the last 5 years, basically everyone has retracted that claim. I've certainly heard Lenny say that complementarity, and this was a result of the firewall story, which showed some inconsistencies in Lenny's earlier claims and so on. So I think it's probably fair to say that everybody agrees we have no idea what's going on now. Some people will still, on occasions, make extreme statements about how they think might work, but the field is in a very different state now. So as far as a Kuhnian or even a Galisonian revolution in how we think about it, that's clearly not on the table now because we don't.
Well,
there isn't really even a consistent set of hypotheses about how things
I
work.
understand. I understand. The issue is again up for debate. However, the conclusion that's drawn on the basis of this firewall debate is not, oh, you know what, we've been wrong, so therefore let's revert back to the position of information being lost. Instead, so I kind of skipped through this, no. Yeah, this is what people say, right?
Okay, but you took there the two most extreme people out of 1,000 people working on this subject. That is not a representative of.
So who the people whose names are here?
They're talking about.
This is the response.
No. Oh, this is. I thought that you were quoting them about the firewall.
No,
I see.
this is about the firewall. But this is what people
Yeah.
take away from the firewall, right? The response is not, oh, you know what? Let's go back to information being lost. No, the response is, well, let's fix this. Let's safeguard unitary evolution because that's baked into ADS-CFT. As ADS-CFT is so important that we need to. So yes, I mean, if your point is. It's now not the case that everybody believes that black hole complementarity is a solution, sure. However, this tells me that people really would like unitarity to prevail.
That is true.
Maybe we should just...
I think it's fair to say that, in fact, as far as I know, and I've made this statement in a number of talks, there are only two people who would put their money on unitarity, and you had their pictures up there, Unruh and...
On non-unitarity.
On non-unitarity.
Yes. Well, and that again fits...
That may be true, but that doesn't mean the other 998 people think they know what is going on.
I fully take your word for it, yes. Yeah. But knowing exactly what does happen in black hole evaporation is something else perhaps than believing that unitarity will prevail in the end.
Yeah.
Let's be brief because I know everybody's had a long day.
So actually, I'm glad you mentioned that, Andy, because I was going to say, wait, there are at least two people who think who don't think there's a problem. But actually, what I want to say though is something of a follow-up to what Priya asked. So it's not so, and in some ways, actually, it's also a sequela to what Andy asked. So if you ask a particle physicist, someone really trained in the particle physicist tradition, what's a black hole? Mm-hmm. They'll say, well, it's an excitation of a certain kind. It's a certain kind of excitation of a quantum field. Yeah. And if you ask a relativist, they'll say, well, it's the past of the causal boundary of future null infinity. And it's very, very difficult, just prima facie, to see how those two ideas fit together. But are you saying? But it's not clear to me though. How the choice between one or the other, ways to think about it, is a choice of values. Can you say more about why it is that? My training really was as a relativist. I tend to think of black holes as the boundary of the causal past of future null horizons. But I recognize that as somewhat contingent. But I don't really see it as a value choice. It's an incredibly useful thing to do.
Well, I mean, either position. Hinges upon certain principles in theory, right? And there's a bit of a sort of a slide here from principles in theory to values. However, the point is that the sort of the decision process is much more like a weighing of values because it has to do with who you are professionally. That's why this judgment that eventually takes place, because you make a judgment, you pursue a certain theory on the basis of this kind of a judgment. And that judgment is more like a value judgment than, say, a deductive argument.
We will continue this over beers. And Avi, can I do a last question?
Yeah, I just wanted to point out, perhaps I'm unusual in that regard, but the reason I'm proud to be a physicist is because the truth is not dictated by a majority vote. It's not a matter of how many people, in one camp believe that they are right versus how many people in the other. We don't count the number of people. What matters really is whether we describe reality, okay? And to me, it sounds like we are still at a state where we haven't gotten, nobody would have thought of quantum mechanics without the experiments that led to it. If you would have made a poll among the physicists back then, they would never come up with quantum mechanics. So it seems to me like what we are missing is some feedback from nature in the form of experiments that will guide us. And in this temporary state that we are at, we can fight back and forth and never be convinced that what is the truth.
Like, I didn't use the T word. I didn't say, you know, one position is true, and I also don't think that you know, that's not what's driving this debate. If you look at it as an historian, right? Like, you know, I'm not trying to educate who's, you know, being, who's converging to the truth. Sorry, I forgot the. Oh yeah, the empirical.
The lack of data.
Yeah. Sorry. So to come back to the empirical, the thing is, you know, if you kind of study the history of science, then often, you know, the empirical doesn't actually lead, right? The empirical is more like something that comes after a lot of theoretical work. I mean, Copernicus versus Kepler, or sorry, Copernicus versus Ptolemy. You know, that didn't look exactly like, you know, Copernicus had to be right because there was this clear observation that told him to put the sun in the center of the solar system.
In the case of quantum mechanics, it was.
Yeah, quantum mechanics is an example of a theory that you know, was very strongly empirically driven, indeed, yes. So you know, it's not a black and white picture.
On this non-black and white picture, I think I'd like to call the meeting to an end, to thank Nina and Bill for their great help in organizing things, to the collaborators on the Black Hole Initiative, to all of you coming from far and wide. It's been a wonderful occasion, and we look forward to seeing you in the future. Thank you.
Thank you.